Hi, and welcome to lecture 2. I'm hopeful that you'll watch this before the lesson on Tuesday when you're going to have a substitute, and you're going to be working on handout 1 and the second page of these notes. So what I wanted to start off with is our first type of linear programming model that we use. It's actually one that's similar to Farmer Jones, and so I'm hopeful that this kind of model will, it's one of the most fundamental ideas. It's basically you need to make, there's some sort of producer and they have to decide what to make. Each of the things they make requires a certain amount of objects. Now, there's a number of pitfalls that occur here that are subtle, and so I really want, my goal is for all of us to get to a place where we never make these sort of the typical sorts of mistakes. So I'm going to try to point that out as I go along with this. Okay, so here we have Shiny Bright. It makes 2 brands of toothpastes, normal and tartar control. This was actually taken from the 2013 final I wrote a while ago. Shiny Bright uses 3 ingredients to make toothpaste: sweetened paste, silica gel, and sodium fluoride solution. To make 100 grams of normal toothpaste, it requires 60 grams of paste, 30 grams of gel, and 10 grams of solution. To make 100 grams of tartar control toothpaste requires 50 grams of paste, 35 grams of gel, and 15 grams of solution. Shiny Bright has 5,000 grams of paste, 3,500 grams of gel, 1,000 grams of solution available. They receive a profit of $1 for every 100 grams of normal toothpaste and $1.20 for every 100 grams of tartar control toothpaste. Remember, one of our standing assumptions is that we don't assume discrete variables where you're assuming continuous, that Shiny Bright can indeed sell all, can sell fractional amounts of toothpaste. I understand that that's not realistic, but it's the kinds of models we're using now, so toothpaste. And we're also going to assume it can sell all. It sells everything it makes. Okay. All right, so with that in mind, let's start. The first thing we do in any model, we have to figure out what our decision variables are going to be. Now, there's a lot of choices here. I'm going to give you, and based on what we need, we want to go with as few variables as we can get by with, really. And then maybe we need to add some later. So we need to think, what are the decisions and what are the results of those decisions? And sometimes the results of those decisions do need to be understood, but the real thing we need to keep in track of are, in this first model, what is sort of the simplest model possible? That's usually the easiest thing. So when we look at this, you can see that there's normal and tartar control toothpaste. There's also this paste, gel, and sodium fluoride solutions. So what you're trying to identify in a resource allocation model are what are the products being made and what are the resources. The products being made are always have to be decision variables, and they drive everything else. The resource used, sometimes you need to keep track of that, but you don't always. And so you should try to first model without keeping track of that. It turns out you can usually get away without ever using them. It just might make your model look a little bit clumsier. So because these are the products, these are indeed the things we're going to use as our decision variables. So I'm going to label them N equaling normal toothpaste made, and this is in 100 gram quantities, and T, which is going to be equal to tartar control made in 100 gram quantities. Now, it is required for you in models in this class for you to write out what, you need to describe. This is required. You need to describe what decision variables are used. Okay. So now with these decision variables, we're going to be able to write out our objective. In this case, we want to maximize. Let's see, it's $1 for every normal made, so I'll just put N plus 1.2 times T. and this is the profit. It's also required to label what you're doing. This is not mathematical, by the way. These labels, these definitions are not part of the math. They're what connects the math to what we're doing for modeling. They're for English, people who, in the case of us, are speaking English. They're for people to read, okay? Your model is useless unless it is communicated to people. Now to indicate we're gonna start our constraints, I write subject to, and we can start to abbreviate that as S period T period. Means the same as subject to. S period T period sometimes means such that. In this class, it's going to mean subject to. We'll use a different symbol for such that. So it's subject to. Well, let's see. We have a constraint on paste. So, and this is where people get into trouble. Sometimes they say, it's tempting to say, something along the lines of, does N equal 60p plus 30g plus 10s for paste, gel, and solution? And no, it does not. And the way you can tell this is wrong, now if you look at how it's read, like when you read it, that's how it's read. 100 grams is made out of 60 grams of paste and 30 grams of gel and 10 grams of solution. That's certainly how it looks when you read it. But this is how English and reading the English can confuse us. It's not, we have to be very careful. And the way you can test it mathematically is just plug in P equals 1, G equals 0, S equals 0, right? Just plug in that, and suddenly that yields 60 equaling N. Frown face, that's not right at all. Okay, so we know this idea is wrong. We don't want it. You should always be able to test out your constraints, and they should always make sense. Okay, so what would make sense? Well, it turns out that we have to think about for the paste constraint, I'm going to write the label over here so I don't get to the side. And it doesn't matter if you write it on the left or the right for the label, that you're going to have 60 grams of paste for every 100 grams of normal toothpaste you make. Plus, you need 50 grams of paste for every tartar you make. And that all has to be less than or equal to the paste on hand. And we have 5,000 grams of paste on hand. Okay. Note that I don't write the units in these because this is just mathematical expressions. Okay, so we don't need the units here. We're going to have a similar constraint for gel. This is going to be 30 grams for every normal, 100 grams of normal, plus 35 grams for every 100 grams of tartar. And that has to be less than or equal to 3,500. Note, I'm using less than or equal to and not strictly less than. If you use strictly less than, I will be very sad as I mark off points off you because I don't want to have to mark off points of you, and neither do you. So let's not do that mistake, okay? Then we have solution, and why not? We don't do that because a strictly less than is not a linear program, okay? We have to have less than or equal to. For solution, we see that 10 grams for every 100 grams of normal, plus 15 grams for every 100 grams of tartar, and this is less than or equal to 1,000, okay? And then we have N and T are non-negative. And that's the first resource allocation model that we've called it that. It turns out, if you think about what Farmer Jones is, very similar model, right? In this case, our resources were flour and eggs, and our products were chocolate and vanilla cakes.